Good morning, everyone. Last class we have done the rectangular window, and today we will continue with the remaining three windows: the Hamming window, Hanning window, and the Blackman window that are present in your syllabus. Actually, there are many other windows also, but all are not present in the syllabus in your curriculum. So only these four are present. So we'll continue with the Hamming window. First, let me share the screen. Okay, now I think you are able to see. So this was the introduction of the digital filters. So now we'll move the note. Okay. So this was the rectangular window part, and so today we'll be continuing the Hamming window. So you see, like rectangular window also, Hamming window is a type of window, and it's given by Wn equal to 0.54 minus 0.46 cos of 2 pi n by m minus 1. M is the length of the FIR filter, and the range will be for Wn, the range will be minus of m minus 1 by 2, which should be less than or equal to n, which is less than or equal to m minus 1 by 2. And Wn will be 0 in any other part otherwise. Okay, now frequency response for this window, will be, it's actually WH. Hamming window is denoted by WH, and in case of Hanning window, the next part, you will see I have written W suffix HANN. So this way we differentiate the two types of windows. So WH e to the power j omega equal to 0.54 sine of omega m by 2 by sine omega by 2 plus 0.23 sine of omega m by 2 minus m pi by m minus 1 by sine of omega by 2 minus pi by m minus 1 plus 0.23 omega m by 2 plus pi m by m minus 1 by sine of omega by 2 plus pi into pi by m minus 1. Clear? Now, this is actually the frequency response of Hamming window. Now, for m equal to 25, if the length of the digital FIR filter is 25, then the window sequence of Hamming window for m equal to 25 will be like this, you see. And below the window sequence, you have got the frequency response of the Hamming window. This is the diagram for frequency response of the Hamming window. And again, the log magnitude response of the Hamming window. Okay. So these are the three diagrams. Just you have to know. And it is obvious from the above diagrams, you see, that the peak side lobe level is down about 41 decibel from the main peak. You see, the peak side lobe level is down about 41 decibel, this one, in the log magnitude response from the main peak. Okay, so this is all about Hamming window. Now we come to the Hanning window. In Hanning window, the causal Hanning window function is given by WHANN, I told you, of n equal to 0.5 into 1 minus cos 2 pi n by m minus 1 for n is greater than equal to 0 and less than equal to m minus 1, or W of n equal to 0 otherwise. Okay, the non-causal Hanning window is given by WN equal to 0.5 plus 0.5 cos of 2 pi n by m minus 1. Okay, where n will be greater than equal to 0, less than equal to m minus 1 by 2. Actually, for causal and non-causal, you see the ranges are different, nothing else. So the frequency response of non-causal window will be what? Wn e to the power j omega equal to 0.5 sine omega m by 2 by sine omega by 2. plus 0.25 sine omega m by 2 minus pi n by n minus 1 by sine omega by 2 minus pi by n minus 1 plus 0.25 into omega m by 2 plus pi n by m minus 1 divided by sine of omega by 2 plus pi by m minus 1. Okay. Now again, for m equal to 25, you see actually the labeling is done wrong. Okay. The labeling is done wrong. It will be Hanning. Okay. This one will be Hanning. This labeling will be Hanning window. Actually, both are diagrams are same. Windowing diagrams are same for both Hamming and Hanning window. So this labeling, it is wrong in the book. It will be Hanning window. Just I have taken the snapshots from the book. Okay. So this is about the frequency response, and this is about the log magnitude response. Clear? Of Hanning window, you see, and Hanning window it is written. Okay. And it is written correct, but this one will be Hanning. Okay. Now come to the Blackman window. So for Blackman window, the causal Blackman window function is WB n equal to 0.42 minus 0.5 cos 2 pi n by m minus 1 plus 0.08 cos 4 pi n by m minus 1, where n is greater than equal to 0, less than equal to m minus 1, or equal to 0 otherwise. And the non-causal window is given by WBN equal to 0.42 plus 0.5 cos 2 pi n by m minus 1 plus 0.8 cos 4 pi n by m minus 1 for n greater than equal to minus of m minus 1 by 2 less than equal to m minus 1 by 2 or equal to 0 otherwise. Now you see again for m equal to 25, the window sequence, it is almost same as the Hamming and Hanning window. This is the frequency response of Blackman window, and this is the log magnitude response. This one is the log magnitude response. Okay. Now for Blackman window, the main lobe width, you see the main lobe width for frequency response in the frequency response diagram is given 12 pi by m. Okay, main lobe width is 12 pi by m. The peak side lobe is down about by 57 decibel. You see, this one is minus 57. So this is the main lobe. It is down side lobe by 57 decibel. Okay, these all are the side lobes almost, and this is the main lobe. So this is minus 57. That means it is down by 57 decibels. Clear? Okay. Now come to a part called ripple ratio. So what is ripple ratio? The ripple ratio is actually a ratio of the maximum side lobe amplitude by the main lobe amplitude. Maximum side lobe amplitude by main lobe amplitude. Okay. And if you are asked the percentage ripple ratio, then this ripple ratio into 100 will give you the percentage ripple ratio. Okay. Now you can see in my note, I've given a table like structure, important frequency domain characteristics. So the 4 windows that we have come to know right now, related to that 4 windows, I have collected some information in GIST for that, so that it is easy for you to remember and memorize rather than. So you see, for rectangular window, the main lobe width is 4 pi by m. Minimum stop band decibel is minus 21. Peak amplitude of the first side lobe is minus 13, and percentage ripple ratio is 22.34%. Okay. For Hamming window, main lobe width is 8 pi by m. Minimum stop band decibel is minus 44. Peak amplitude of the first side lobe is minus 31, and percentage ripple ratio is 2.62%. For Hanning window, main lobe width is same as the Hamming window, 8 pi by m. Minimum stop band minus 53. Peak amplitude of the first side lobe minus 41, and percentage ripple ratio is 1.47%. And for Blackman window, the main lobe width is highest, 12 pi by n. Minimum stop band decibel is -74. Peak amplitude of the first side lobe is -57, and the ripple ratio is the least, 0.08%. So the above table, what it shows? The above table shows that main lobe width is highest in Blackman and lowest in rectangular, and percentage ripple ratio is maximum in rectangular and minimum in Blackman. That means main lobe width and this ripple ratio percentage are inversely proportional to each other. Since rectangular window has the least main lobe width, so it has the highest percentage ripple ratio. And for Blackman window, vice versa. It is having the highest main lobe width and the percentage ripple ratio is the least, 0.08% only. Okay. So these all are the theories related to the windows. Clear? Now, in the previous class, I've told you that I'll be doing numericals related to impulse invariance and the bilinear transformation method, isn't it? So first, let us see some steps, actually. Steps used for designing IIR filter using impulse invariance. Means if you're given a problem, what are the steps that you should follow? What are the steps that you should follow? You see, first, determine normalized analog filter HS that satisfies the specifications for desired filter. In the second step, expand HS using partial fraction expansion method. In the third step, obtain the Z transform of each term formed by partial fraction expansion method. And the fourth one, last step, is obtain HZ by combining Z transform in step 3. Clear? This is the steps for designing an IIR filter using impulse invariance. Now, steps for designing an IIR filter using bilinear transformation, what they should be. You see, from given specifications, find the pre-warping analog frequencies using the relation this ohm p star equal to 2 by t. Star means pre-warp frequency, isn't it? 2 by t tan of ohm p t by 2. Using analog frequencies, find HS of the analog filter. In the third step, sampling rate of the digital filter is to be selected. And fourth step, substitute S equal to 2 by t into Z minus 1 by Z plus 1 in transfer function HS. Then obtain design digital filter. Clear? So now let us come across a problem. You see, an analog filter transfer function is given by HS equal to 1 by S plus 3 into S plus 5. So obtain transfer function HZ of IIR filter using impulse invariance method. Assume t equal to 0.1 seconds. Okay, so our first work in this case will be to split HS into the partial fraction expansion method. HS equal to 1 by S plus 3 into S plus 5, which is equal to A by S plus 3 plus B by S plus 5. Clear? Now using partial fraction, A comes half, B comes minus half. Okay. Now I'm taking let C1 equal to half, C2 equal to minus half, P1 equal to minus 3, P1, and P2 equal to minus 5, suppose. Okay. Now, what is HZ for impulse invariance method? It is summation of k equal to 1 to 2 ck by 1 minus e to the power pk into t z to the power minus 1. So ck, k is 1 to 2, means there are two C1 and C2. That's why k equal to 1 to 2. So half, C1 is half, C2 is minus half. Just we have replaced the values. And pk also p1, p2. So 1p is for minus 3, 1p is for minus 5. So you can find in the two terms. Then simplifying those two terms, we get half into e to the power minus 3t minus e to the power minus 5t into z inverse by 1 minus e to the power minus 3t plus e to the power minus 5t into z inverse plus e to the power minus 8t into z to the power minus 2. Now, at it is told that assume t equal to 0.1 seconds in the question, isn't it? So at t equal to 0.1, we replace the values of t at point 1, and again you find hz. So hz comes as 0.067 z inverse divided by 1 minus 1.3473 z inverse plus 0.449 z to the power minus 2. So this is our hz. Clear? So this is the problem. We have found out hz. Now come to the next problem using bilinear transformation. So design a digital filter using bilinear transformation from the analog filter given by HAS equal to HAS means the analog filter A equal to 1 by S square plus root 2S plus 1. The question is obtain digital filter by assuming 3 decibel cutoff frequency of 150 Hz and sampling frequency 1.28 kilohertz. Clear? Okay. Now cutoff frequency is 150 Hz. So what will be omega? Omega is 2 pi f. So 2 pi into 150 means 300 pi radians per second. Okay. Now time will be the inverse of sampling frequency. So what is the sampling frequency? 1.28 into 10 to the power 3. So time will be 1 by 1.28 into 10 to the power 3. Now we have to calculate what? The pre-watt frequency, isn't it? So what will be our pre-watt frequency? Pre-watt frequency is omega p star equal to 2 by t tan of omega p t by 2. So omega p star is what? 2 by t. T is 1 by 1.28 into 10 to the power 3 tan omega p t by 2. What is omega p? Omega p is 300 pi by 2 into 1.28 into 10 to the power 3, which comes as 987.3. Okay, so 987.3. Now, pre-watt analog filter is H star S equal to HS at S equal to S by omega p star. Now, HS is what? 1 by S square plus root 2S plus 1. At S equal to S by omega p star is 987.3. So in this equation of HS, replace S by 987.3. So we get, after replacing, we get 1 by 1.02 into 10 to the power minus 6 S square plus 1.43 into 10 to the power minus 3 S plus 1. Now we will find HZ, Z transform. So what will be HZ? HZ will be H star S at S equal to 2 by T into Z minus 1 by Z plus 1. Now again replace S by 2 by T into Z minus 1 by Z plus 1. And on solving HZ we get 0.0878 into 1 minus 2Z inverse plus Z to the power minus 2 divided by 1 minus 1.0048 Z inverse plus 0.3561 Z to the power minus 2. Clear? So this is the two problems related to impulse invariance and bilinear transformation method and the steps that I have written. So kindly follow those steps and it will be very easy for solving. It's very easy. Now, you see, related to the choice of windows, if I ask which window is better, Hamming window or Hanning window? So what will be your answer? You see, both. Why did I ask this question? Because both Hamming window and Hanning window have the same transition width. However, Hanning window generates less ringing in the side lobes, and so it is most widely used. Means Hanning window is advantageous than Hamming window. Clear? The Blackman window reduces the side lobe level at the cost of increasing transition width. Okay. Now, what are the advantages of designing window for FIR filters? Listen, if you want, you can write down, note down also. I'll be telling very slowly. You see, point number one will be the filter coefficients can be obtained with much less computation. Point number two, the window functions are readily available in suitable form, as we have seen. Direct form is available. And point number three, almost complete removal of ripples in both passband and stopband is possible using these windows. So these are the advantages of using windows for designing FIR filters. Now, if you use windows, there are some disadvantages also. What are the disadvantages? You know, what are the disadvantages? You see, a closed form expression for the Fourier series coefficients, Hn, may not be always obtained. Windows design offers limited flexibility in design. Means you cannot change the type of filters much if you use Windows. Flexibility is lost. And the third point is sometimes it is difficult to determine the type of window in advance, as also the duration M capital M, what is it? It is the length of the FIR filter to meet given prescribed frequency specifications. Okay. So these all are the advantages and disadvantages of using Windows. So today I've discussed the remaining three windows, the ripple ratio, and the advantages and disadvantages of using Windows for FIR filter design, and problems related to bilinear transformation and impulse invariance, along with their steps. Clear? So that's all for today. Thank you.